We're going to talk about logarithmic functions today. So in all likelihood, this is something that you've never heard of before. We're going to start with a little summary about inverse functions. So inverse functions were on test 2. So this is a pretty long time ago that we talked about inverse functions in general. So here's just a little summary, facts about inverse functions that you should remember. So only one-to-one functions have inverses that are functions. You test if the graph of a function is one-to-one by using the horizontal line test. Right? Everyone remembers that? Okay. If a function of one-to-one, its inverse function can be found by swapping x and y and solving for y. So that's how you find a formula for its inverse function. The domain of f is the range of f inverse, and the range of f is the domain of f inverse. So the domain and range swap. And the graph of f inverse is the reflection of the graph of f about the line y equals x. That is, to get points on the graph of f inverse, you just swap the x and y coordinates on the graph of f. And because inverse functions undo each other, when you compose two inverse functions, you get x back. So f of f inverse of x is the same thing as f inverse of f of x. Both of them give you x back. All right, so if any of this is unfamiliar, at some point you should go back and probably reread the section in chapter 2 about inverse functions. It would help you review for the final also. All right, so if you remember from last class that an exponential function, f of x equals b to the x, is one-to-one, right? Passes the horizontal line test. No matter what value we choose for b. Sweep a horizontal line through here, never touches more than once. So that means it has an inverse function, right? Because it's one-to-one, we know it has an inverse. So on the graph of 2 to the x that I put down here, we want to sketch the graph of the inverse function, the inverse of 2 to the x. So to get an inverse function, you just swap x and y coordinates. So I'm going to pick a few key points on here, like 0, 1, 1, 2, 2, 4, and 3, 8. And maybe 1 over here, maybe I'll do -1, a half. Okay, so I swap the coordinates and plot them. So instead of -1, a half, I'm going to have a half, -1. And instead of 0, 1, I'm going to have 1, 0. Instead of 1, 2, I'm going to have 2, 1. And instead of 2, 4, I'm going to have 4, 2. Instead of 3, 8, I'm going to have 8, 3. And I'm going to connect all these with a nice smooth curve. And you can see that the curve I drew is the reflection of 2 to the x over the line y equals x. So this guy is the inverse of y equals 2 to the x. What do you think its formula is? Formula for that pink curve. Yep. So that's how you find formulas for inverse functions. We start with y equals 2 to the x. We interchange the x and the y. And then we have to solve for the y. So I have x equals 2 to the y. If it was y squared, I would take the square root. Yeah, how do you undo 2 to the y? How do you get the y by itself there? The y root. Well, if I had replaced x with something, if x were a number instead of a plain old x, right? If I had like 10 equals 2 to the y. If I took the y root, over here, we think that we'd get 2, right? The y root of 2 to the y would be 2. And we still have the y root of 10, so I still don't have y by itself, right? So that can't be it. So we actually don't have a way to do it right now. We don't have a mathematical way to solve the equation that we wrote, this x equals 2 to the y. All right, so we need some way that will undo 2 to the y and give me the y back, right? If I take the y root, I get the 2 and the y's cancel, and I don't want that. So I need some way to undo 2 to the y that will just give me the y. All right, so go with me. This is brand new and weird looking. We're going to call the thing that undoes 2 to the y log base 2 of y. All right, so I'm going to write x equals 2 to the y. And I'm going to take log base 2 of both sides. No. So this is going to be log base 2 of x equals log base 2 of 2 to the y. All right. So we just invented this thing. Okay, we're calling it log base 2. We just made it up. We're just saying we need something that will undo 2 to the y. We're going to call it log base 2. And when you take log base 2 of 2 to the y, you get y. That's our definition. Right? We just made it up. And that's going to equal log base 2 of x. So this is the equation of the inverse function that we sketched. Log base 2 of x. What? This is like a little much, right? Okay. So let's go back and be a little bit more precise about what this thing is. So if x is positive and b is positive, but not 1, y equals log base b of x is equivalent to the equation b to the y equals x. So any two equations are equivalent if you can make one into the other, right? So like, just like 10 over x equals 5 is equivalent to 10 equals 5x, those two equations are equivalent, right? Or y equals x and y equals 5x over 5, those two equations are equivalent, right? These two equations are equivalent. For any base b, y equals log of x is equivalent to b to the y equals x. All right, so I'm going to use this definition. We're just going to practice using this definition a little bit. I've given you some statements in log form, right? I've given you what it looks like this, and I want you to change it to what looks like this, b to the y equals x. All right, so 2 equals log base 3 of 9. What is b in this equation? 3. Okay, so I've got 3 to the something equals something. So b to the y. So what is y in this equation? 2. And that should equal 9, which it does. So log base 3 of 9 equals 2 is exactly the same as saying 3 squared equals 9. These are just two different notations for expressing the exact same information. Okay, you try this one. Write it in exponential form. Okay, so looking at this equation, this is my base b, a little 8, right? And the thing that's on the other side of the equal side from the log is my y. And then this thing I'm taking the log of is my x. And my definition of a log says that if you have y equals log base b of x, that's equivalent to b to the y equals x. So I'm going to have 8 to the negative 1 equals 1/8. Is that true? Yeah, good. So these are, again, two equations that are equivalent. They express the same information in a different way. All right, so now I want to write, now I'm giving you an exponential equation, and we want to change it to a log equation. So let's write these as identify our b, y, and x. So this 2 is my b, 3 is my y, and 8 is my x. And then plug it all into this other equation, y equals log base b of x. So 3 equals log base 2 of 8. So one easy thing to remember is that the base in both of the equations is the same. So if you have log base b or b to the y, b is your base in both equations. And then the x's and y's switch places, which makes sense because a log and an exponential are inverses, so the x's and y's should be swapping. So here I have 6 to the negative 2 is 1 over 36. So this should say log base 6, because the base in my exponential is 6. And in this case, now my negative 2 and my 1 over 36 swap places. Log base 6 of 1 over 36 equals negative 2. So there's nothing super conceptual right now. All I'm doing is introducing this new definition of what it means to be a log. It's the inverse of an exponential, and we're just doing some symbolic manipulation, switching things around to create equivalent equations. All right, so now we're going to evaluate each of these logs, and it can make it easier to write an equivalent exponential equation, right, to answer a log question. So this is log base 10 of 100 equals what, right? So if I change this to an exponential equation, this says 10 to the x equals 100. Well, what do you raise 10 to make a 100? 2, yeah. So log base 10 of 100 is 2. Okay, log base 5 of 1 over 125 equals what, right? We don't know, so we'll call it x. Well, this, if I rewrite it as an exponential equation, would have base 5 raised to the x equals 1 over 125. Close. It is a negative exponent, but it's not the negative fifth. Closer. Third. 5 cubed is 125. So 5 to the negative 3 is 1 over 125. So in this case, x would be negative 3. All right, you try to answer this one. Log base 36 of 6 equals what? Okay, so if I want to change this to an exponential equation, my base is 36. My log base 36, that's my base and my exponential also. To what power will give me a 6? 1/2, yeah, because the square root of 36 is 6. And another way to write a square root is to the 1/2 power. So here x is a half. All right, so some basic log properties. Log base b of b. I want to figure out what this is. See, I'll do it on another page. Oops. Log base b of b equals what, right? Yep, so b to the x equals b, right? I've got my base raised to the x equals b. What does the exponent have to be? B to what power gives you b? First. Okay, so we go back over here. Log base b of b is always 1. All right, let's think about log base b of 1. Log base b of 1 equals what? So this says b to the x. Base b to the has to be 0. Good. So no matter what base I'm working with, log base anything of 1 is always 0, because anything to the 0 is 1. All right, how about log base b of b to the x? Yes. So x has to be, let's write it out. log base b of b to the x equals what, right? I'm using a question mark instead of an x because there's already an x in there. All right, so this says b to the question mark equals b to the x. So what does my question mark have to be? X. Yeah. So log base b of b to the x gives you x back. And this is because logs and exponentials are inverses. This is a composition of log base b of something and b to the x. You plug one into the other, you should get the x back. They're inverses. So in that same line of thought, what is b to the log base b of x? It's x again. We'll write it all out. B to the log base b of x. Oops. Log base b of x is what? All right, so this is an exponent. This is b to some stuff equals a number, right? If I were to write this in log form, I would have log base b of question mark equals log base b of x. So what's my question mark have to be? X. Oops. And again, this is because those two functions, b to the x and log base b of x, are inverses. So if you compose them in either direction, like we did in C or in D, you should get the x back. So there are two special bases, 10 and e. Okay, so 10 is called the log base 10 is called the common log or the common logarithm because we work in a base 10 number system. So powers of 10 come up a lot. So we call this log base 10 the common log. And we often don't even write the base in there. So instead of writing log base 10 of x, we just write log of x. And you just assume that the 10 is there. So if you ever see a log without the base showing, it's a base 10. And if y equals log of x, that means 10 to the y equals x, just using the definition. And then our other special base is e, because like we talked about last class, e shows up as the base in a lot of exponential functions. So having a logarithm to undo e to the x makes sense. And we call it the natural log. So it's log base e of x, which we abbreviate ln x. But you might think, why don't we abbreviate it natural NL for natural log? But I think it's because abbreviation was created by a French mathematician, and in France, the adjective comes after the noun, right? So we would say the natural log, and they would say the log naturel. I'm writing the L first. Yeah, that makes sense. Yep. So we abbreviate log base e of x with ln x. So if y equals ln x, that means e to the y equals x. These are the only two log buttons you have on your calculator, base 10 and base e. So I'm just going to show you where they are. Okay, so your log buttons are here and here along the left side. So if you want to take log base 10 of something, you just type it in, log of 100. We already did this a little while ago. We know the answer should be 2, right? Yeah, because 10 squared is 100. And if I want to take, say, the ln of 20, you just type it in, and that means that e to this power should give you 20. So I can always check e to the 2.995732274 should give me 20, very close to 20, because it must have rounded. There must be more decimals. Right? It just won't fit in my screen. All right, so now we're going to do a little bit of practice of both doing things by hand and using the calculator. So I want to evaluate each of these logarithms by hand, right? Just think about what the answer has to be, and then check by using your calculator. And the last one, you can't be accurate when you do it by hand, but you can come up with like a guesstimate. All right, so I want you to work on those for a minute or two. Okay, so log of 1,000. That is asking you what power should you raise 10 to make 1,000, right? Because there's no base showing, so you have to assume there's a little base 10 there. And that equals something, right? So this is saying 10 to what power will give me 1,000. And what does x end up being? 3, yeah. So log base 10 of 1,000 equals 3. How about log of 0.01? -2, yeah, because 10 to the -2 is 0.01. ln of e cubed, right, is something, right? So this is asking me, because it's ln, it's a base e, that's just hidden there. So this says e to what power will give you e to the third power? Right, so x is 3 here. So the ln of 1 over e squared. This is asking me what power should I raise e to get 1 over e squared? The -2, yeah. Because e to the -2 is 1 over e squared. All right, the ln of 5, this one's a little harder, right? Equals something, I don't know what. This is asking e to what power will give me a 5. Well, what's e to the first? 2.7 something, 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 right? So it's not 1. X isn't 1. What's e squared? 7 something, yeah. So it's somewhere between 1 and 2. So that's all I can say without using my calculator to help me. Between 1 and 2. So I have to use my calculator to finish this problem. So I just type ln of 5. And I get 1.61 is the ln of 5. And I can check all of my answers using the calculator. The ln of 1 over e squared is -2, just like we got. And the ln of e cubed is 3. And the log of 0.01, so I use my log button here, 0.01, -2. And the log of 1,000 is 3. So those are the only 2 log buttons you have in your calculator. So if I give you a base other than 10 or e, you have to do it by hand for now. All right, so now let's take a look at the graph of some log functions. We already sketched the graph of y equals log base 2 of x because we started with 2 to the x and we reflected it over the line y equals x. So these 2 graphs are inverses of each other. So we did that a little bit earlier. So these 2 pictures illustrate the relationship between the graph of an exponential function and its inverse, which is a logarithmic function, for bases greater than 1 and bases between 0 and 1. So here's bases greater than 1. We've got exponential growth. Reflect that over the line y equals x to get the inverse. And that is the graph of log base b of x. Y equals log base b of x. And then here's the graph. When b is between 0 and 1, you get exponential decay, the blue graph. Reflect over the line y equals x, and you get y equals log base b of x. All right, so looking at both of these, well, we're looking at the pink graph, just the pink graph in both of these pictures. What is the domain of the log function? Looking at both, no. Yep, it approaches the y-axis as an asymptote, never crosses. 0 to infinity, not including 0 because it approaches this y-axis. So that's my asymptote, x equals 0, which is the y-axis. Because the exponential function had a horizontal asymptote of the x-axis, and when you reflect that over the line y equals x, you get the vertical axis. All right, looking at my pink function here, what is the range of this function? All y values, yeah. Negative infinity to infinity. Yep, it lives on all y values because it goes down forever and it grows forever. And this kind of makes sense because the domain and range of the exponential was all reals and its range was 0 to infinity, so they swapped. Is this pink graph one-to-one? Yes. Does it have any extrema? Does it have a y-intercept? No, because it approaches the y-axis but never touches it. How about an x-intercept? 1, 0. And end behavior. Well, in my two different flavors, I have two different end behaviors. So in this, when b is bigger than 1, my graph approaches infinity, right? And as x approaches 0, right, because as I go to the left, I can't pass the y-axis. So I'm just going to say what happens as I get close to 0 is I go to negative infinity. And this is for b bigger than 1. When b is between 0 and 1, those switch. So let's write that down. As x approaches infinity, y approaches negative infinity. And as x approaches 0, y approaches infinity. And this is for b's between 1 and 0. Okay, so here's the graph of log base 2 of x. And we sketched this earlier in class, right? Like one of the very first things we did. We go back to it so you can see it. Here was 2 to the x. I reflected it over the line y equals x. And this is the graph y equals log base 2 of x. So we did that. Very first thing we did in class today was we sketched that graph by sketching the inverse of 2 to the x. All right, so I want you to use log base 2 of x as the parent function. So I've given you the parent function, both of these. I want to sketch each transformation. So if I want to sketch log base 2 of quantity x plus 3, what transformation is taking place here? It's a shift, but it's horizontal. It's inside, right? I'm changing the x that's getting plugged in. So this is a horizontal shift, 3 to the left. So that means that my asymptote that used to be at 0 is now going to be at negative 3. And then I can pick a few key points and move them all 3 to the left. Right, so this point at 1, 0 is going to go 1, 2, 3 to the left and be right there. And then I've got a point 2, 1. Move it 3 to the left, and it's going to be at negative 1, 1. And let's see, I have 4, 2 is going to end up at 1, 2. And 8, 3 is going to be at 5, 3. And when I connect these, I'm going to have a graph that looks something like that. Just shift the whole thing left 3 units. All right, what if I want to sketch the graph of negative log base 2 of x? What kind of transformation is that? A flip over which axis? The x-axis, yeah. This is an outside change, right? I'm changing the y value, which means all my y values are going to be opposite, so it's going to flip over the x-axis. So my asymptote stays right where it is. Everything just flips. So y values are going to switch. So instead of that's going to stay where it is because it's 1, 0, and the opposite of 0 is still 0. And then this point at 2, 1 is going to become 2, negative 1. And 4, 2 will become 4, negative 2. 8, 3 becomes 8, negative 3. So this is going to look like that. A reflection over the x-axis. All right, so we learned earlier today that the domain of a log function is the set of positive real numbers, or 0 to infinity. Right, we did that right here. We wrote down that the domain is 0 to infinity. Okay, what do you think the domain of log base 4 of x minus 3 is? Yeah, because whatever I'm taking the log of has to be bigger than 0. Right? So x minus 3 has to be bigger than 0, which means x has to be bigger than 3. Because the log function can only take numbers between 0 and infinity. So you have to make sure that whatever you're taking a log of has to be bigger than 0. So my domain would be 3 to infinity, not including the 3, because you can't take the log of 0. All right, so that about covers everything about log functions. I want you to spend some time now working on this activity, logarithmic laptops.